everybody. Good morning. Myself, Dr. Shubhankar Sen, an associate professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the third lecture of Module 5 of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall derive the shape functions for the linear triangular elements in global coordinate system. So we have already discussed the Pascal's triangles. Here we show part of the triangle. So this is x to the power 0, y to the power 0. This is x, this is x square, and so on. Here we have y, then we have y square, and so on. So if we join the term x, y and x to the power 0, y to the power 0, then the triangle which we obtain, this is known as the linear triangular element. So for the linear triangular element, we have 3 nodes. So this particular shape with nodes 1, 2 and 3, we say that this is a linear triangular element when we have 6 nodes. Then we say that we have a quadratic triangular element. So this is a linear triangular element, and this is a quadratic triangular element which has 6 nodes. So this is element E, this is also element E. Its nodes are 1, 2, 3, 4, 5 and 6. In today's class, we shall consider the linear triangular element in the global coordinate system, and we shall find out its shape functions using its global coordinate data. So in the xy plane, we consider an arbitrary linear triangular element E with local nodes 1, 2 and 3. So this is the origin of the global coordinate system. So global coordinates of nodes 3 are identified as x1e, y1e, x2e, y2e and x3e, y3e. In 2 dimensions, a polynomial can be expanded as, in 2D, a polynomial can be expanded as txy equals to a plus bx plus cy plus dxy plus ex square plus fy square and so on. Now, if we consider only the first 3 terms, then we get a linear polynomial in 2 dimensions. The product xy, this is a quasi-linear term which we find in case of a bilinear quadrilateral element. So when we restrict our data with a, b and c, or with x to the power 1 and y to the power 1, then we deal with linear polynomial. So this portion represents a linear portion in 2 dimensions. Now, for the linear triangular element, we have 3 nodes. With 3 nodes, we can write 3 algebraic equations and we can solve for 3 coefficients. For example, the coefficients can be a, b and c. Now, here we have written the polynomial directly in terms of the degree of freedom temperature. So let us consider a linear variation of DOF T equals to Txy in 2D. This can be expressed as Txy equals to A plus Bx plus Cy, where A, B and C are constants, and this portion represents a complete polynomial in linear scale. Now we can represent the trial solution Txy also in terms of Tje, psi je, xy, where j is varying from 1 to nen. For a linear triangular element, nen equals to 3. So nen equals to 3 for a linear triangular element. So we can write it as T1e psi 1e xy plus T2e psi 2e xy plus P3e psi 3e xy. Now satisfy the Txy equals to A plus Bx plus Cy function at each node of the element. At node 1 we have T x1e y1e equals to T1e. So let us define temperatures at these nodes as T1e, T2e and here as T3e. So T at x1e y1e equals to T1e equals to A plus B x1e plus C y1e. Similarly at node 2 T at x2e y2e equals to T2e equals to A plus B x2e plus C y2e, and finally at node 3 T at x3e y3e equals to T3e equals to A plus B x3e plus C y3e. So we get a system of 3 simultaneous or coupled algebraic equations with A, B and C as the unknown quantities. So this gives us a system of 3 coupled algebraic equations for unknown A, B and C. In matrix form, we may write 1 x1e y1e 1 x2e y2e 1 x3e y3e into the unknown vector A, B, C equals to T1e, T2e and T3e. A, B and C can be found out by using Cramer's rule. Cramer's rule is a direct method of solving the unknowns for small matrices. So we don't use Cramer's rule for a big size matrices because the operation count in Cramer's rule it increases in a very large way. So the operation count for Cramer's rule it is represented as factorial of n plus 1 where n represents the size of the matrix. For a matrix of size n by n, so when we talk matrix we certainly mean a square matrix. Operation count for Cramer's rule is factorial n plus 1. This being a large number for moderate to high values of n, Cramer's rule is never used for matrices of higher size. So Cramer's rule is a direct method of solving Ax equals to B matrix equation system. Okay, so using Cramer's rule we obtain A divided by T1e, T2e, T3e, X1e, Y1e, X2e, Y2e, X3e, Y3e equals to B by 1, 1, 1, T1e, T2e, T3e, Y1e, Y2e, Y3e equals to C by 1, 1, 1, X1e, X2e, X3e, T1e, T2e, T3e equals to 1 by determinant of the matrix if we denote the matrix as capital A. So let us denote this matrix as capital A. So determinant of this matrix is the last term, determinant of matrix A. So we can simplify this as A equals to determinant of T1e, T2e, T3e, X1e, X2e, X3e, Y1e, Y2e, Y3e divided by determinant of A. This we can simplify as T1e into X2e, Y3e minus X3e, Y2e minus X1e into T2e, Y3e minus T3e, Y2e plus Y1e into T2e, X3e minus T3e, X2e divided by determinant of A. Similarly, we can find B equals to determinant of 1 T1e, Y1e, 1 T2e Y2e 1 T3e Y3e divided by determinant of A equals to T2e Y3e minus T3e Y2e minus T1e into Y3e minus Y2e plus Y1e into T3e minus T2e divided by determinant A, and similarly C equals to determinant of 1 x1e T1e 1 x2e T2e 1 x3e T3e. This can be simplified as 1 into x2e T3e minus x3e T2e minus x1e into T3e minus T2e plus T1e into x3e minus x2e minus x2e divided by determinant A. So we have evaluated the unknown constants A, B and C. So we can write the trial solution Txy equals to A plus Bx plus Cy. This we can write it as our A was determinant of T1e, T2e, T3e, x1e, x2e, x3e, y1e, y2e, y3e divided by determinant of A plus Bx. So B was 1, 1, 1, T1e, T2e, T3e, y1e, y2e, y3e divided by determinant of A into x plus Cy. So this is our C term where we had 1, 1, 1, x1e, x2e, x3e, T1e, T2e, T3e into y. This can be written as Txy equals to 1 by determinant A into T1e into x2e, y3e minus x3e, y2e minus x1e into T2e, y3e minus T3e, y2e plus y1e into T2e, x3e minus T3e, x2e. So this is the constant part of A. Next contribution is Bx. So here we get plus 1 into T2e y3e minus T3e y2e minus T1e into y3e minus y2e plus y1e into T3e minus T2e into x, and finally we have 1 into x2e T3e minus x3e T2e minus x1e into T3e minus T2e plus T1e into x3e minus x2e into y. Now the coefficients of T1e, T2e and T3e, we will segregate them. So this gives us 1 by determinant A into T1e into x2e y3e minus x3e y2e. So from the first contribution, this is the part coefficient of T1e. Now let us go for the B term and search for the T1e contribution. So here we get T1e into y2e minus y3e into x. Then we go for the third term, the contribution coming from C. There we find that this is plus T1e into x3e minus x2e into y. So here we have combined all the terms appearing with T1e. The next we go for T2e. So here we get 1 by determinant of A into T2e. If we look into the terms from small a, then we get for T2e we have x3e y1e, x3e y1e minus x1e y3e, x1e y3e. In the B term we have for T2e as plus T2e into y3e minus y1e. So this is y3e minus y1e into x. Then from the C term we get T2e into x1e minus x3e, x1e minus x3e into y, and finally we get 1 by determinant A to T3e. From the A portion, small a portion, we get with T3e we have x1e y2e, x1e y2e minus x2e y1e. Next we go for the x term T3e into, in the intermediate term for T3e we have y1e minus y2e. So we have y1e minus y2e into x, and for the y term we have finally T3e into here we have x2e minus x1e. So we have x2e minus x1e into y. So we can write them as T1e psi 1e xy plus T2e psi 2e xy plus T3e psi 3e xy. Here psi 1e xy equals to 1 by determinant A into x2e y3e minus x3e y2e plus y2e minus y3e into x plus x3e minus x2e into y. Then we have psi 2e xy equals to 1 by determinant A into x3e y1e minus x1e y3e plus y3e minus y1e into x plus x1e minus x3e into y and psi 3e xy equals to 1 by determinant A into x1e y2e minus x2e y1e plus y1e minus y2e into x plus x2e minus x1e into y. Now our matrix capital A, it was 1 x1e y1e, 1 x2e y2e, 1 x3e y3e. So its determinant is given by determinant of A equals to 1 into x2e y3e minus x3e y2e minus x1e into y3e minus y2e plus y1e into x3e minus x2e. Now these are our shape functions with respect to global coordinates. So shape functions of linear triangular elements with respect to global coordinates. Now, for a linear triangular element with local nodes 1, 2 and 3 and coordinates x1e, y1e, x2e, y2e and x3e, y3e, area of element A is given by area equals to half into x1e into y2e minus y3e plus x2e into y3e minus y1e plus x3e into y1e minus y2e. This area, it represents half the value of determinant of matrix A equals to half of determinant of A. Therefore, det A equals to twice the area of the linear triangular element. Now we have the shape functions expressions. Using these expressions, we can find out the shape function for triangular elements of regular shape. It means that when the included angle of the triangle, one of them is 90 degree, or a right angle triangle with two of the edges being parallel to the Cartesian coordinate axis. So shape functions for right angled triangular elements with two edges parallel to or aligned with the Cartesian coordinate axis. So let us first consider this example of a linear triangular element with local nodes 1, 2 and 3. This is the triangular element E. The global coordinates are x and y. So this coordinate is 0, 0. This edge is of a length, so the coordinate is a0, and the vertical edge is of length b unit, so that its coordinate is 0, b. So the dimensions, they are a and b. So area of the triangle equals to half into a into b equals to ab by 2. From here, we can understand that for this case, the matrix which is constructed by the coordinates of this element, this will give us the determinant value of AB. Therefore, determinant A equals to det A equals to AB by 2 into 2 equals to AB, where A equals to 1 x1e y1e 1 x2e y2e 1 x3e y3e. So these are 1 0 0 1 x2e and y2e. x2e is a, y2e is 0 1 x3e, that is 0, and y3e, that is b. So we can see that its determinant value is AB. This is twice the area of the triangular element. This gives us determinant of A equals to AB. Now we have x1e equals to 0, y1e equals to 0, x2e equals to a, y2e equals to 0, x3e equals to 0, and y3e equals to b. So we have the coordinates and we have the expressions that we have written in the previous page for the shape functions. Using these expressions, we can calculate the shape functions. So psi 1e xy equals to 1 by determinant A into, we have the expression here, x2e y3e minus x3e y2e, x2e y3e minus x3e y2e. Then we had y2e minus y3e into x, y2e minus y3e into x, and finally we had x3e minus x2e into y, x3e minus x2e into y. This is the expression for psi 1e. So by putting these values we get determinant A, this is AB, so 1 by AB, x2e, this is A, and y3e is B, minus x3e is 0, y2e is also 0, plus y2e minus y3e into x. y2e is 0 and y3 is b, so it is 0 minus b into x, plus x3e minus x2e into y. x3e is 0 and x2e, this is a, so 0 minus a into y. So this gives us 1 by ab into ab minus bx minus ay. This can be written as 1 minus x by a minus y by b. Now we can have the expression for the second shape function. Psi 2e xy equals to 1 by determinant of a into x3e y1e minus x1e y3e, x3e y1e minus x1e y3e, plus y3e minus y1e x, y3e minus y1e into x, plus x1e minus x3e into y, x1e minus x3e into y. We can write this as psi 2e xy equals to 1 by ab, determinant a is ab, x3e is 0, y1e is also 0, minus x1e is 0, and y3e is b, plus y3e minus y1e into x, y3e is b minus y1e, this is 0, into x, plus x1e is 0, minus x3e is also 0, into y. So this gives us bx by ab equals to bx by ab equals to x by a. Then we are left with the last step function, that is psi 3e xy. This is also 1 by determinant of a into the expression is x1e y2e minus x2e y1e, x1e y2e minus x2e y1e, plus y1e minus y2e into x, y1e minus y2e into x, plus x2e minus x1e into y, x2e minus x1e into y. This gives us as 1 by ab into x1e y2e. x1e is 0, y2e is 0, 0 into 0, minus x2e is a, y1e is 0, so 0 into a into 0, plus y1e minus y2e. y1e and y2e both are 0, so 0 minus 0 into x, plus x2e minus x1e into y. x2e is a and x1e is 0, so it is a minus 0 into y. So this is ay by ab. This comes as y by b. Therefore, we have obtained all three shape functions for the right angle triangle with two of the edges aligned with the Cartesian axis. So we can summarize these expressions for this triangular element. So this is 0, 0, this is A0, this is 0B, this is our y-axis, this is our x-axis, this is element E, local node 1, local node 2, local node 3. So we have obtained psi 1e x, y. These are the global coordinates, shape functions with respect to global coordinates, equals to 1 minus x by a minus y by b. 1 minus x by a minus y by b. Psi 2e x, y, x by a, and psi 3e x, y equals to y bar b. Therefore, we can check these properties of these Lagrangian shape functions, these triangular elements. These are Lagrangian elements or C0 elements, and the shape functions are also C0 continuous, so the temperature will be continuous at the nodal point, but not the temperature gradient. So we can just check the summation of the shape functions. Summation of psi ie x, y, I is varying from 1 to any n equals to psi 1e x, y plus psi 2e x, y plus psi 3e x, y. These we find as 1 minus x by a minus y bar b plus x by a plus y divided by b equals to 1. So it satisfies the property of Lagrangian shape function. And another property we can check with respect to the psi 1e. Psi 1e at x2e, y2e, or psi 1e at local node 2, this will be 1 minus x2e by a minus y2e by b. So 1 minus our x2e, it is a, so it is a by a. Our y2e is 0, so it is 0 by b. So it is 1 minus 1 minus 0. So this is 0. Similarly, psi 1e at x1e, y1e equals to 1 minus x1e by a, y1e by b. x1e and y1e both are 0 valued. So this gives us 1 minus 0 by a minus 0 by b equals to 1, and psi 1e at node 3, x3e, y3e, it should be 0. So this is 1 minus x3e by a minus y3e by b. So this is 1 minus 0 by a minus b by b equals to 1 minus 0 minus 1 equals to 1. Therefore, the shape functions satisfy the properties of Lagrangian shape functions. Now, for the regular triangular elements of linear type, we can similarly calculate psi 1e, psi 2e, and psi 3e. So, I am showing some pictures of the conventional triangular elements that have a right angle and edges parallel to the Cartesian coordinate axis. So, I suggest that you calculate the psi 1e, psi 2e, and psi 3e for such elements. So, common right angle linear triangular elements for which shape function can be calculated as shown above. So we can consider this is a triangular element in the xy coordinate system. So local node 1, local node 2, local node 3. So this base is of dimension A and this height is of dimension B. Similarly, this is case 1. Similarly, we can have some other triangular elements. We can have triangular elements of this shape. So this is element E. This is local node 1, local node 2, local node 3. This is the x-axis. This is y-axis. So this is 0, 0. So this is A, B, and this is 0, B. So this height is B and this length is A. So here this is certainly 0. The expressions that we have calculated for obtaining shape functions of linear triangular elements with nodes 1, 2, and 3, I emphasize that these expressions are valid for linear triangular elements of any shape. We have illustrated the example for a simple shape of right-angled triangles, but these expressions are valid for triangular elements of linear type irrespective of their shape. Now we correlate the arbitrary shaped triangular element with the master triangular element for linear type. Consider an arbitrary linear triangular element and also consider the linear master triangular element. So in the global coordinate xy, we have an arbitrary shaped triangular element E, local nodes 1, 2, 3. Its actual coordinates are x1e, y1e, x2e, y2e, x3e, and y3e. This is the global origin 0, 0. Now in the natural coordinates xi eta, we have a corresponding master element which is a right angled isosceles triangle. The master linear triangular element is a right angled isosceles triangle. So here the local nodes are identified as 1, 2, 3 with coordinates 0, 0. This is 1, 0 and this is 0, 1. So this is the master element. This is the physical or actual element. So we have 1-to-1 mapping from the physical plane to the master plane. 1-to-1 mapping from the physical plane to the natural plane. This implies that the edge 1, 2 in the physical coordinate system is precisely matches with edge 1, 2 in the natural coordinate system. So this transformation, it is valid at the edges as well as within the domain of the element. So there is an 1-to-1 transformation with 3 nodes of the element. So since the element is of linear type, the transformation from x and y to xi and eta, it can be represented as the x to xi or y to eta transformation can be represented as x equals to a plus b xi plus c eta and y equals to a dash plus b dash xi plus c dash eta. Now, using the actual coordinates of the physical element in the xy plane for nodes 1, 2 and 3, we can calculate the coefficients a, b, c or a dash, b dash, c dash. So let us consider the x coordinate data. So consider x coordinates of element E in the physical plane and let us solve for A, B and C. At node 1, x equals to x1e, this is A plus B xi, xi is 0, so B into 0 plus C eta. At node 1, eta is also 0, C into 0, this gives us A equals to x1e. At node 2, we have x2e equals to A plus B xi plus C eta. So A is already calculated as x1e plus B into xi, xi is 1 plus C eta, our eta is 0 corresponding to local node 2. So this is C into 0. So this gives us B equals to x2e minus x1e. Now at node 3, our x coordinate is x3e. So x3e equals to A plus B xi plus C eta. Our A is x1e, our B is x2e minus x1e. At node 3, the xi coordinate is 0. So x2e minus x1e into 0 plus C eta, eta is 1. This gives us C equals to x3e minus x1e. So we have the solutions for A, B and C in terms of the global x coordinates of the actual element. Therefore, A equals to x1e, B equals to x2e minus x1e, x2e minus x1e and C equals to x3e minus x1e, x3e minus x1e. Now, x equals to A plus B xi plus C eta gives x equals to x1e plus x2e minus x1e into xi plus x3e minus x1e into eta. This gives us x1e into 1 minus xi minus eta plus x2e xi plus x3e eta equals to x1e psi 1e xi eta plus x2e psi 2e xi plus x3e psi 3e xi eta. So this is equals to summation of xje psi j as a function of xi and eta, where j equals to 1 to nen equals to 3 for a linear triangular element. So therefore, we represent the shape functions in the natural coordinates for the linear triangular element as psi 1e xi eta equals to 1 minus xi minus eta, psi 2e xi eta equals to xi, and psi 3e xi eta equals to eta. Using these shape functions, we can now calculate the Jacobian matrix for an arbitrary triangular element. The Jacobian matrix for the linear triangular element may be obtained as JE. It will be a 2 by 2 matrix in 2 dimension. Del x, del xi, del y, del xi, del x, del eta, del y, del eta. This gives us JE equals to del xi into summation of xj psi j, j equals to 1 to 3, del xi into summation of yj psi j, j equals to 1 to 3, del eta summation of xj psi j, j equals to 1 to 3, and del eta of summation of yj psi j, j equals to 1 to 3. So this is a 2 by 2 matrix. Now expanding, we can write x1e del psi 1e del xi plus x2e del psi 2e del xi plus x3e del psi 3e del xi. Here we have y1e del psi 1e del xi plus y2e del psi 2e del xi plus y3e del psi 3e del xi. In the second row, we have x1e del psi 1e del eta plus x2e del psi 2e del eta plus x3e del psi 3e del eta. The last term is y1e del psi 1e del eta plus y2e del psi 2e del eta plus y3e del psi 3e del eta. Now we can substitute the derivatives here. x1e, now del psi 1e del xi, here we can see del psi 1e del xi equals to -1. So this gives us -1 plus x2e del psi 2e del xi. This gives us del psi 2e del xi equals to 1. So x2e into 1 plus x3e into del psi 3e del xi, it is equals to 0. So del psi 3e del xi equals to 0. So x3e into 0. So here in the 1, 2 term, we get y1e into del psi 1e del xi, we just calculated it as -1 plus y2e del psi 2e del xi, this is 1, and del psi 3e del xi is 0. So this is y3e into 0. In the second row, first term, we have x1e into del psi 1e del eta. So del psi 1e del eta is -1. Del psi 1e del eta, it gives us minus 1. So this is minus 1 plus x 2e del psi 2e del eta. This is 0. So del psi 2e del eta equals to 0. So x2e into 0 plus x3e into del psi 3e del eta. Del psi 3e del eta is 1. Del psi 3e del eta equals to 1. So x3e into 1. In the last term of this matrix, we have y1e, the same derivatives we have, del psi 1e del eta, it is already minus 1, plus y2e del psi 2e del eta, it is 0, and del psi 3e del eta, this is already found as 1. So we can simplify the Jacobian matrix as x2e minus x1e. Here we have y2e minus y1e. In the second row, we have x3e minus x1e, x3e minus x1e, and the last term, it reduces to y3e minus y1e, y3e minus y1e. Therefore, determinant of the, this is a 2 by 2 matrix, Jacobian matrix is obtained as determinant of Je equals to x2e minus x1e into y3e minus y1e minus x3e minus x1e into y2e minus y1e. So we can write it as determinant of Jacobian equals to x2e minus x1e, x2e minus x1e into y3e minus y1e, y3e minus y1e minus x3e minus x1e, x3e minus x1e into y2e minus y1e, y2e minus y1e. So this is x2e into y3e minus y1e minus x1e into y3e minus y1e minus x3e into y2e minus y1e plus x1e into y2e minus y1e. So this can be written as x2e into y3e minus y1e minus x1e y3e plus x1e y1e plus x3e into y1e minus y2e plus x1e y2e minus x1e y1e. Now x1e and y1e, they are of opposite sign, so they cancel out. So this can be written as x1e into y2e minus y3e plus x2e into y3e minus y1e plus x3e into y1e minus y2e equals to 2 into half of x1e into y2e minus y3e plus x2e into y3e minus y1e plus x3e into y1e minus y2e. Now, this expression, we have already discussed that it represents the area of the triangular element. Area of the triangular element. Therefore, the determinant of the Jacobian of an arbitrary triangular element, this is twice the area of the given element equals to 2 times area of the element. So we had the Jacobian matrix as JE equals to X2E minus X1E at the first term, X2E minus X1E. The second term was Y2E minus Y1E, Y2E minus Y1E. In the second row, we had X3E minus X1E, X3E minus X1E, and Y3E minus Y1E. So this was the given Jacobian matrix for an arbitrary triangular element. Now, the inverse of the Jacobian matrix, this can be easily obtained here. The inverse of the Jacobian matrix is equals to 1 by determinant of J into Y3 minus Y1E, Y1E minus Y2E, X1E minus X3E, and finally here X2E minus X1E. So this inverse is a 2 by 2 matrix. This inverse, the entries are denoted as J11 tilde, J12 tilde, J21 tilde, and J22 tilde equals to JE inverse. This is also a 2 by 2 matrix. Now we have already the interpolation functions in the actual coordinate system for an arbitrary element x, y. This is element E, this is 0, 0, this is A0, this is 0B, this is local node 1, local node 2, local node 3. For this element, we found that psi 1 E xy equals to 1 minus x by a minus y by b. Psi 2 E xy equals to x by a, and psi 3 E xy equals to y by b. Now, when we go for the master triangular element, this is the master triangular element, the isosceles triangle. This is xi, eta, local node 1, local node 2, local node 3. This is E cap, the master plane. Now here we have psi 1 E, xi eta equals to 1 minus xi minus eta, psi 2 E, xi eta equals to xi, and psi 3e xi eta equals to eta. So if we compare these expressions, then we find that xi scales with x by a, or non-dimensional streamwise distance, and eta scales with y by b, the non-dimensional cross-stream distance. So this is we obtain by comparing. Comparing these two cases. So some bracket will come inside. We conclude our class here. In today's class, we have determined the shape functions for linear triangular elements in 2 dimensions. we have used Cramer's rule to evaluate the coefficients during calculations. We have also shown the shape functions in the natural coordinate system. For today's class, I suggest the textbooks authored by Professor T.J.R. Hughes as well as Professor J.N. Reddy. Thank you very much for attending this class.